Okay, so directional derivatives and gradient vectors. Alright, so let's say we have we consider some function, two-dimensional function, at a point a comma b. Then the derivative, the partial derivative of f with respect to x at that point gives the slope in the direction of the vector 1, 0. And the reason why this is because we have the partial derivative of this function with respect to x. Just take my word for that right now. Similarly, if I have the partial with respect to y at the point AB, then that gives the slope in the direction of the vector 0, 1. Alright. So, what about in the direction of some unit vector? Which we denote as u sub 1, comma u sub 2. What if we want to find the partial derivative in some specific vector direction? Well, so a directional derivative excuse me. A directional derivative, to get an idea of what this is and what it is, we're going to make a little graph. So hey, I'm using a gift card as a ruler. Because guess what? My ruler's at school. So that's x, that's y, and that's z. Okay. So let's say we have a curve. So let's say this curve looks like something like this. So this curve is actually coming, it's coming out towards you. So that's why I put dash lines here, because it's in the back right there. And let's just say we have a vector that looks like this. Here's the unit vector. Right? Now, if I have some random point on my curve, so if I have some point on my curve, So this right here is the curve z equals f of xy, and I'm going to adjust this. There we go. That looks a little bit better. So how do we define the directional derivative? How do we do it? Well, here's what we do. So, note. If we have a point P, A, B on the function f at x comma y, in the direction of the unit vector u equals u sub 1 comma u sub 2, then so let me just write this out. Let me just write this out, and then I'll do what it means graphically. So if we have a point P sub A on the function in the direction of u, then the directional derivative of f of xy at, and that's important, at the point P of AB and in the direction of the unit vector This might seem redundant, but just bear with me. So if we have this stuff, then we could say, all right, comma, then the directional derivative of the function at this point and in the direction of here is defined as, or is given by, so we denote it as capital D sub u of the function at a comma b, and that equals the partial derivative of f at ab times u sub 1 plus the partial derivative of y at ab. Oh shit, I ran out of frickin' space. Sorry for my language. Times u sub 2. So let me write this down here. One of the drawbacks of not using a whiteboard is I can't erase it, huh? So that's d sub u of f at ab equals the partial of f with respect to x at ab times u sub 1 plus the partial of f at y at ab times u sub 2. That looks a little bit better. So sorry about that, guys, but this right here is directional derivative. So, that's how you find the derivative, or the directional derivative of a function at a particular point in a particular direction. So, let's just say that let's say the following here. So, here's my unit vector. Here's my function, right? So, let's say I have the point on my curve. Let's say the point is over here somewhere. So then if I want to find the directional derivative of this function at this point in this direction, well, it's going to, whatever that rate of change is, it's going to be pointing in this direction, right? Its rate of change will just be the slope in that particular direction. So it'll be pointing in that particular direction. So that right there will be the directional derivative at this point. So the directional derivative of u at that point will be the slope of f of xy at AB in the direction of u. So that's what this represents, but this is the vector. That right there is the directional derivative there. So this is the vector that corresponds to it, but at this particular point, right, it'll be pointing in that direction. But it's important to note that the directional derivative it's not a vector, but it's a scalar, right? So note, the directional derivative is a scalar. It's not a vector. So this at this particular point it's going to be the slope in a particular direction. That's what it's going to measure. In a particular direction, it'll be like a value of the slope at a particular direction of a given vector. And that's what the directional derivative is. That's what it represents. So, I've showed you how to calculate it. And I know this might not seem the most straightforward way, but that's basically what's going on. Okay. So, why don't we look at an example here. If f of xy equals e to the 4x squared minus y power, comma, find the directional derivative of f of xy at the point 1, 4 in the direction of -2, 1. Okay, so just like I wrote, this is how you compute the directional derivative. So we're computing this, right? So that's f of sub x, the partial of x, with respect to x, I mean at AB times u1, the partial with respect to y at AB times u2. So that's what we're trying to compute. Right? Okay, well, so let's go through that. So I need a unit vector, right? I need a unit vector. So, all right, well, how do we find a unit vector? So how do we find a unit vector? So if you remember from, this is all the way back when we find unit vectors, we take the given vector that we have and we divide it by its magnitude. So this will be negative 2 comma 1 divided by the magnitude of negative 2 comma 1. Right? So the magnitude of that vector is the sum of its squares of the square root, so that's going to be negative 2 squared plus 1 squared, which, so that's going to be 1 over the square root of what? That's going to be 4 plus 1, which is 1 over the square root of 5, times negative 2 comma 1. So the unit vector is going to be equal to, I'll just bring the 1 over square root of 5 inside, negative 2 over root 5, comma 1 over root 5. All right, so that's the unit vector. Okay, but now I want to find, so the components of the unit vectors are right here, right? U sub 1, U sub 2. This right here is U sub 1. This right here is U sub 2. Okay, so now I just need to find the partial of the function with respect to x, and then the partial of f with respect to y. And then what I'm going to do is I'm going to plug in the given point into those partial derivatives. Okay, so here's my function, right? So, all right. So compute the partials. All right. So what's the derivative of this with respect to x? Y is going to be held constant, right? So, well, so you could think of this as like e to the 4x squared minus a number, right? How do you use that? Use the chain rule. All right. So you're going to use the chain rule here. So you're going to take the derivative of the whole thing. So that's going to be e to the stuff. The derivative of that's going to be e to the stuff times the derivative of the stuff. Now with respect to x, it'll be what? 8x minus a number, so that'll be 0. So that'll be 8x, right? So that right there is the partial derivative with respect to x. Now do it with respect to y. Alright, well, we're going to still use the chain rule. It's going to be e to the stuff. But now, it's going to be times the derivative of the stuff. Now with respect to y, this is a constant. So we're going to have a constant minus the derivative of this, which would be negative 1, right? So that'll just be negative 1, right? Okay, so those are my partial derivatives. Now what I want to do is I want to evaluate the partials at the given point, right? That's what these parts are going to be in the directional derivative formula, right? So I want to find the partial of with respect to x at the point 1, 4, and the partial with respect to y at the point 1, 4. So plug that into each partial. All right, this is 8x times e to the 4x squared minus y, and this is negative e to the 4x squared minus y. Excuse me. All right. So when you plug in 1 and 4 in here, what do you get? You're going to get 8 times 1. So you're going to get e to the 1 squared minus 4. For 1 squared minus 4. So when you go through that, what do you get? Well, so 1 squared is 1, so 4 times 1 is 4, 4 minus 4 is 0, e to the 0 is 1, so I'm going to have 8 times 1, which is going to be 8. And then when I plug this into the partial with respect to y, I'm going to have negative e to the 4, 1 squared minus 4. So, like we already said, this is going to be e to the 0, which is 1. So, with a negative, it's going to be negative 1. Okay. So, these values right here correspond to these right here. So, if I want to make this star in this box, that's star, that's box. So now it's just a matter of computing them. So therefore, the directional derivative in the direction of u at the point 1, 4 of this function equals, so the partial of f with respect to x at 1, 4 was 8. So this is the dot product. So that's going to be this, right? That's what this is. This is dot product between this and that. So that's going to be 8 times the u1 component of the unit vector, which is negative 2 over root 5, plus negative 1 times the u2 component of the unit vector, which is 1 over root 5. All right. And when you go through that, that's a basic computation. You get negative 16 over root 5 minus 1 over root 5, which is what? We'll use our calculator here. That. Plus negative 1 divided by root 5. That. So you could do it in your calculator, but when you do this, you should get negative 15 divided by root 5. Or, no, not negative 15 over root 5. Negative 16. What am I missing? Negative 17 over root 5. I think that sounds better. Yeah. So when you do the computation here, right, 8 times negative 2 is negative 16 over root 5 minus 1 over root, so negative 16 minus 1 is negative 17 over root 5. So that right there is the directional derivative. Like I said, it's a scalar. So that is the slope at this point. So let me make a note of that. This value represents the slope of f of xy, which was defined up here, at the point 1, 4 in the direction of -2, 1. So that's what this value represents. It's a directional derivative. It's basically if you're on some surface, right? If you're on some surface, right? And it's basically saying how fast are you changing instantaneously in a particular direction on that surface. So if you can imagine yourself standing on like a hill, like if you go hiking in the mountains, right? You know, how fast are you walking along that hill, right? Because when you walk along a hill, you're going in a particular direction on a hill, right? So how fast are you going at a particular moment walking on that hill? That's what this is measuring. So, you know, it's really not that bad. It's pretty straightforward, but that's how you compute the directional derivative. So, okay. Well, this leads us to a pretty important concept in this course. So this is perfectly fine for using the directional derivative, but there's a more efficient way we could describe this. So these two partial derivatives, x and y, they represent a particular function. Well, they represent a particular vector, I should say, of this function. And that's called the gradient vector. And that's pretty important. So the gradient of the function xy is the vector function. Now the gradient is a vector. It's a vector function, so obviously it's a vector. So the gradient of f of xy is the vector function. So it's denoted as the following. It looks like an inverted triangle of f at xy, and that equals, so instead of, you know, writing it out in component notation, it's just the partial of f with respect to x, comma, the partial of f with respect to y. So that right there is the gradient of a function. And you can see that, right? This is a function, right? And the gradient of the function gives me a vector. That's why it's a vector value function. So this is a vector. The gradient of f is a vector. Whereas the directional derivative is a scalar. So this inverted triangle has a particular name. Before that, this is an assumption that we make, but this is true provided both partial derivatives exist. And usually we assume that to be true, but you know, it is an important side note. So the notation del f, well, I just said it. The notation inverted triangle f, I'm going to say what it is read as. It actually has a few interpretations. It's usually represented as grad f. And I'm going to use that from time to time. Or it could be written as del of f. That's another, that's another way of saying it. So, you know, you could say that this is read as del of f. That's perfectly fine. Or you could say grad of f. I typically use grad of f. I don't know, del just always sound goofy to me, so I typically use grad. So yeah, grad of f, and it's obviously grad because it's short for gradient. So, all right. So, provided we have this notation now, we could say, all right, there's an alternate form of the directional derivative. Instead of writing it out in component notation, we could just write it out with gradient notation. So instead, we have a alternate form of the directional derivative, which is as follows. So we could write the directional derivative now we could write this instead as grad of f at xy times the vector u. This is the same thing as that. Same thing. But instead of using component notation, now we could just write it as a whole vector. And this is a dot product, right, between two vectors, and the dot product between two vectors is a scalar. Hey, one of the first few things we talked about in this course. All right. So now you know what the gradient looks like, and the alternate form of the directional derivative. That's you know, it's pretty useful. So we could extend this before I go to the next page. You know, we can extend this idea to three variables. So how would this look with three variables? Well, so if we had a three variable function, if w was equal to f at xyz, so this would be a certain, not just a surface, but a shape, right, a volume. If that is a differentiable function, and u is any unit vector, well, we have the directional derivative in the direction of u of a given function at a particular point. It's not hard. It's just you tack on an extra coordinate. You tack on the z coordinate. So it's just grad of f x comma y comma z dot u, where the unit vector is u1, u2, u3, and grad of f. So what would the gradient of f look like now? Well, the gradient of f would be, well, if this is the gradient of f xy, then the gradient of f of xyz, you just tack on another, it would be df partial of f with respect to z. So it would be the vector partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. You know, sorry about this. This is butchered right here, but this is the word extend. This. I wrote extended by accident. But, yeah, so, I mean, this is the directional derivative in the 2 variate and 3 variate case. So, for a surface or a volume. A surface in R2 or a shape in R3. Alright, so this is like a plane. This is like a, you know, an ellipsoid or a sphere or whatever kind of shape. Alright, let's look at another example here. So, 3-variate function is equal to cosine xy plus z, and the inputs of this are x and y, not just x. Find the directional derivative at point 0, -2, 4, in the direction of the unit vector (0, 3/5, -4/5). Okay. So, ooh, that's blurry. So in this example, I give you the unit vector. I already gave it to you, so you don't have to find a unit vector. In the previous example, you know, if we go back to the previous example here, I say in the direction of a specific vector. So because that was the case, I needed a unit vector, so I had to make one. But here, I told you that this is a unit vector, so I don't have to find a unit vector. I'm already given one. Okay, so I'm trying to calculate the directional derivative of the function at a given point, and that's equal to grad of f at xyz times u. All right. Okay, so I already have u. I already got this guy. So this guy's taken care of. And now I just got to find the gradient. And then once I find the gradient, I evaluate each, you know, component of the gradient at 0, -2, and 4. And then that'll be this guy. So, okay. So the gradient, right, that's the vector df dx, df dy, df dz. Alright, so what's the partial derivative of this with respect to x? Well, I have a cosine of x times y plus z. Well, z is a constant in this case, and so is y. So I'm using the chain rule here, right? So, you know, if I use the chain rule, the derivative of cosine is negative sine of stuff, right? My stuff is xy, plus the derivative of z, well, that would be the plus 0, right? But now I got to times that by the derivative of the inside stuff. So the derivative of xy with respect to x is going to be y, right? So this will be a factor of y sitting out front with that negative there. So this right there is the partial derivative of that with respect to x. All right. What's the partial with respect to y? Same idea. It's not much different, except this time I'm treating x is the constant, right? So x is going to come out here instead of y. So I'll have negative x sine of xy. And then the derivative of this with respect to z, well, that's really easy. This is a constant. So a constant plus z, the derivative of z is 1, so it's just 1. All right, where's my gradient? Now, I got to figure out my gradient at the given point, which is 0, negative 2, 4. And that'll give me the desired, that'll give me this vector at that particular point. So plug in 0, negative 2, and 4 in here. So, all right, so when you do that, negative 2 goes here, sine of 0 and 4. Well, sine 0 times 4 is 0. Sine of 0 is 0, right? So it doesn't matter. So that's going to be, the first coordinate is 0. Okay, well, x is 0, so it doesn't matter what this is, because 0 times that's going to give me 0 again, and that's 1. Okay, so now I have that. So that is the second piece I needed right here. So now I can compute my directional derivative. So therefore, the directional derivative of the function at the point 0, negative 2, and 4 equals the gradient of f at 0, 2, or 0, negative 2, 4 times u, which is equal to, so it's the dot product between this vector and this vector. Right? Which is what? 0 times 0 is 0, plus 0 times 3/5, plus 1 times negative 4/5, which is, well, that's 0, that's negative 4/5. That's it. So again, what does this represent? This is the slope of this function at this point in this direction. So that's the rate of change. That's the instantaneous rate of change, because that's what the derivative represents. It's the instantaneous rate of change of this function at this point in this direction. So if you could think of this function as like some, I'll use my hiking analogy again. If I go hiking, right, and this is the hill I'm hiking on, if I'm walking alongside the hill, right, I'm moving at a rate of negative 4/5 at some part of the trail on that hill in some direction on that hill. That's what it represents. So, okay. Nothing really tricky about that, but that's the directional derivative there. Okay. So, I'm not quite done with this section yet. I do want to build on some things here. So there are various interpretations of what the gradient of a function represents. So this is some interpretations of the gradient, and they're pretty, they have pretty good significance. So let's say, note, suppose that f of xy is differentiable function at point A comma B. Alright, so I could say one of the following. The maximum rate of change of my function at the point AB is the magnitude of this. That's interesting. So it's going to be the magnitude of the gradient at the point AB, occurring in the direction of the gradient. So that's what this value represents right here. This right here is the maximum rate of change. That's what the gradient really represents. Basically, it's the slope of greatest ascent. So what we did here is not what this is. This is something else. This is a directional derivative. So if I took this right here, right? So if I look back at the previous problem I did, right? This was the gradient at this point, right? So if I had a function at this point, and if I took the magnitude of this vector, so I took the square root of 0 squared plus 0 squared plus 1 squared, I got the square root of 1, which is 1. All right. So here, that means the maximum rate of change of this function at this point would be 1 if I did that here. But this is that value represents something completely different. I already told you what it represents. So if you wanted to find the maximum rate of change, that's what the magnitude or the length of the gradient vector represents. Here's another thing it represents. The minimum rate of change of f of xy at AB is, well, this is the maximum, then the minimum is the opposite of that. So it's just, so if I go in the opposite direction, well, if I have the opposite value of this, it's just going to be negative of this. That's it. And that's occurring in the direction opposite of the gradient. Because what do we know about vectors and their opposite? The opposite vector is just the opposite sign, right? Because a vector is a direction, right? Another thing, the rate of change of f of xy at the point AB is 0 in the directions, here's your favorite word again, orthogonal to the gradient at that point. So if you're orthogonal, basically if you're perpendicular to the gradient at a particular point, then the maximum rate of change, or the rate of change, is going to be 0 because you're not moving in any direction. well, the rate at which you're moving in a direction that's orthogonal to the gradient is going to be 0. So yeah, the fourth thing, the gradient of f at AB is orthogonal to the level curve f of xy equals c. We talked about level curves a while ago. It's like, remember we did contour lines? Well, the gradient is orthogonal to the level curve f of xy equals c at the point a comma b, where c equals f at that point. So all this is saying is if you have like the level curve is like those contour curves we did, then the gradient of the contour curve, or I'm sorry, the gradient of the function at a point is going to be orthogonal to the level curve at that point. And that's all it is. That's all it's saying. They're just going to be orthogonal. Okay. So let's see here. Let's look at an example. Find the direction and values of minimum and maximum change of f of xy equals y cubed sine of x at the point pi comma 1. So you're trying to find the minimum and maximum change of this function. So based upon what I just told you, that represents the gradient of this function at this point. And then you're going to take the magnitude of that vector and you're going to get the value, right? You're going to get the value and we're going to interpret that and say what direction is that going in. Okay, so take the gradient. What does that equal? Well, it's the partial of all the variables you see. So this is two variables. So the first one's going to be the partial with respect to x. So this is a constant. What's the derivative of sine of x? Well, that's going to be cosine of x with the constant sitting out front. So it's going to be y cubed cosine of x, comma. Now the partial of this with respect to y. All right, so now you're going to differentiate this, and this is constant. So you're going to have 3y squared sine of x. Okay, so now the gradient, right, at the point pi 1 is now equal to what? So plug those in here. So cosine of pi, whoops. So cosine of pi is what? -1, so I'm going to have cosine of pi, which is -1, and then I'm going to have 1 cubed, so it's going to be 1 times -1, which is going to be -1 for the first coordinate. And then what's sine of pi? 0. So I'm going to have 0 times, it doesn't really matter, it's going to be 0. Okay. So now I want to find the value that's the maximum and minimum, right? So what do I do now? Now I take the magnitude of this. at that point. Right? So that's just going to be the square root of -1 squared, 0 squared, which is obviously the square root of 1, which is 1. All right, so how do we interpret this, though? So the maximum rate of change is what? It's 1 in the direction, what? In this direction. Right? And then the minimum rate of change, well, the minimum rate of change is the opposite of that. So it's going to be -1 in the direction. So what direction is that going to be in? Well, it's going to be, if this is the opposite of that, right? It's going to be that, but it's going to be in the opposite of the gradient. So what's the opposite? What's the opposite of this? You just multiply it by -1, right? So a -1 times -1 is 1, and -1 times 0 is still 0. You know, nothing tricky there, but that's the basic idea. That's the basic gist of it, guys. Okay. So, you know, let me go back to this level curve thing, because I guess I could elaborate a little better on this. So remember when we did contour lines? Like, you know, so if that was a contour line, and this is a contour line, and so on, right? And let's say this right here is the point AB on a particular contour line, right? So this right here is the curve, right? This right here is the function at that curve, right? So then the gradient at this point will be orthogonal to it. So that right there would be the gradient of the function at AB, and it's going to be orthogonal. You know, I'm trying to make this look like it projects out at a 90-degree angle, but you know, drawing three-dimensional things on a surface is never easy, especially for me. Okay. Let's see here. So, one more thing in this section I want to talk about is, you know, how do I find this particular, you know, how do I find this particular curve to a level curve? Like, how do I find this equation? So this right here would be the tangent line to a level curve, or, you know, what if I wanted to do that? So that's going to be the last thing I want to talk about in this section. Alright, so let's just focus on this part right here. So, So the tangent line to this curve, right? So if I were to make this, as best as possible, right? That would be the tangent line if I were to the level curve. At the point A, B. I know that looks really light. My colored pens are running out of ink. But that right there is what I'm trying to find. So your textbook uses x sub 0, y sub 0. I use AB. I think it's better. I don't know why. It's just me. But so if I want to do that, so I'll jot that down here. So to find the tangent line to a level curve, which we denote as C equals f of xy at the point AB, here's what we do. So it's going to be the partial of f with respect to x at AB times x minus a plus the partial of y with respect to y at AB times y minus b equals 0. So that's how you find the tangent line to a level curve, or like the tangent line to the contour line. And I mean, you could kind of represent this as the gradient of f at AB times x of x minus a and y minus b, but those are this is just a point minus this right here is just, it's not a vector, so using the gradient notation here would not be really necessary. So let me look at a basic example here, and that's really it for this section. So find the equation of the tangent line to the level curve x squared plus y squared equals 4 at the point root 2 comma root 2. Okay, well, nothing too tricky about that. So just keep, I don't need this. I'm just going to move it up here a little bit, but so this right here is my function, right? All right, well, my function, so let me extrapolate this. So the function this is a circle, right, with radius 2. Centered at what point? Well, it's going to be centered at 0, 0, right? So this right here is actually a level curve with a radius of 2, right? But let's just assume that this is not a level curve. Let's just say the function is equal to this in its most generic form. Like I can put any number here. So basically this is just a level curve at 4. But I want the most general form of this curve. So the function is just a level curve for the value c equals 4, right? Because a level curve is where the function equals some particular value, right? That's what a level curve represents, so the function at c. But I don't want that, I just want the function itself. So the function is f of xy equals x squared plus y squared, because this could be equal to, well, in this case it's equal to 4, but it could be equal to 16, 25, or not just a perfect square, but it can equal anything. Okay, so let's compute the gradient of that. What's that going to be equal to? So the partial of this, well, that's easy. Partial of this with respect to x is going to be 2x. Partial of this with respect to y is going to be 2y. All right, now the partial of that at the point root 2. So that's going to be 2 root 2 comma 2 root 2. All right. So now this right here right? So this right here is the partial of f. That's what this value represents. It's the partial of f at the point root 2. And this right here is the partial of y at the point 2 root 2. All right? These markers are getting really light. So those are the values right here. So my equation tangent line to this level curve is going to be, so it's going to be this value, right? Times what? X minus my point A, which was root 2, right? The x coordinate of my point. And then that's going to be plus the partial of y at root 2, which was 2 root 2. And that's going to be times y minus the point at B, which was root 2. And that equals 0. So now from here, you could just, rearrange the, multiply them in and solve for y to get the equation of the tangent line. So when you do, you just do algebra here. So you're going to have what? 2x times square root of 2, just distribute this in. So 2 times root 2 times minus root 2, that's going to be minus. So root 2 times root 2 is going to be the square root of 4, which is 2, right? And 2 times 2 is going to be 4, plus now I'm going to have 2y times root 2 minus, so same thing, 2 root 2 times root 2, that's going to be the square root of 4, which is 2. 2 times 2 is 4. That equals 0. So minus 4 minus 4, that's minus 8. I could bring that over. So I'm going to have 2x root 2 plus 2y root 2 equals 8. All right. Well, I could factor a root 2 or 2 root 2 out of here, can I? We'll have x plus y equals 8. And then I could divide both sides by 2 root 2. So I'll have x plus y equals, well, 8 divided by 2 root 2, which will be what? That'll just be 8 divided by 2 is 4 over root 2. So now if I want, this technically is the equation of the line, but if you want to put this in slope-intercept form, I mean, that's fine, but that right there is the tangent line to the level curve. Okay, so, so this is a circle, right? Centered at the origin with a radius of 2. So the point, root 2, so this is approximately what? 1.41, comma 1.41, right? So if I wanted to approximate that point, that's somewhere in the first quadrant, so that's 2, and that's 2, then, and that's 1, and that's 1, so the 1.4 is roughly there, and there. So this is obviously not drawn to scale, but let's just assume it's right there, right? That's the point. Right? So the gradient of this is going to be perpendicular to that, right? Because I told you about that. It's orthogonal to the row. So the gradient of there is going to be orthogonal to this. So that right there is the gradient of the function at root 2. I know this is kind of bleeding into here, but that's what I'm doing. And now the tangent line to the level curve at that point is going to be tangent to this. With my blue marker that's dying. So that's the equation. X plus y equals 4 over root 2. And, that's the general idea of it. But yeah, that's how you find the equation of a tangent line to a level curve. Hopefully that did make sense a little bit, but that's the idea of how you do it. So that's it for this section. So in the next section, 14.6, we're going to look at tangent planes. How do we find a tangent plane? And how do we find a normal line and a tangent plane, stuff like that. And what does it mean for something to be normal, or things of that nature. And then we're gonna look at a linearization and stuff like that. What does linearization represent? Blah blah blah. And then we're gonna get into finding maximum and minimums. We're going to be doing the second derivative test, finding extreme values of multivariate functions. So that's the end of this section.